Hi, so for today we're going to talk about homogeneous differential equation or homogeneous DE, and we're going to solve some problems involving homogeneous differential equations. And let me first define what is a homogeneous differential equation. In its simplest term, a differential equation is said to be homogeneous DE if every term has the same degree. So that's right, if every term has the same degree. Okay, raised to a certain exponent. If every term has raised to a certain exponent n, and if all the terms are all raised to a certain exponent n, then definitely we have a homogeneous differential equation. So, homogeneous DE can be actually rewritten as the m as a function of x of y dx plus n as a function of x of y dy is equals to 0. So, the m term here is what is actually indicated in the dx, and n here in the term of dy. So is equal to 0. So there is a condition in our solving of homogeneous differential equation. If m is simpler, which means that if this m in terms of x of y is much simpler, we will use the substitution x is equals to vy. And if we get the derivative of this, we have the dx by product rule, we have v dy plus y dv. Again, this dx here is simply the derivative of this. If m is simpler, okay? So actually, you can use any substitution, but it is actually recommended that if you could use the simpler substitution, you use it because it would yield to another. If you use the other one, which is not simpler, it would yield to another integral, which is really hard to integrate. Okay, but you will still arrive at the same answer. Okay, if m is simpler, you're going to use this substitution. It's easy to memorize because if m is simpler, then x is equals to vy. If n is simpler, this function of n and n as a function of x of y, we will be using y is equals to bx. Then the derivative of dy is simply by product rule again, v dx, copy the first, then differentiate the second. So that's why we have v dx here. Plus, again, copy the second, x, and differentiate the v. So dv plus x dv. So m is simpler, use this substitution. If n is simpler, use this substitution. Okay? So I advise you copy those formulas so that you would be able to uh, get not be lost, okay, in our topic. Okay, so for number one, we should be solving, okay, the differential equation x squared minus xy, okay, plus y squared dx, okay, minus xy dy is equals to 0. So this is a homogeneous differential equation because as you can see, we have this term x raised to 2, x squared, which has a degree of 2. Okay, and also the y squared, which has a degree of 2. And xy here, sir, why do we say that this is a homogeneous differential equation? Because the exponent of x is 1, the exponent of y is 1. So if we add them together, since they are in multiplication, okay, still this term, this full term has still a total degree of 2. So hence, this is a degree of 2 for dx. So for dy, that is still the same. Since this is has a degree of 1, still if we add them, okay, the total degree will be 2. So this is a homogeneous differential equation with a degree of 2. And we shall be labeling this as what I have said a while ago, this term as the m, and this term as the n. So as you can see here, m is a function of both x and y, n is a function of both x and y also. So in this case, n is much simpler because it has x and y terms only, unlike this m. So if n is simpler, then we use the substitution let, okay, y is equals to vx, and then differentiate y. So we have v dx plus x dv. So we're going to let these values, okay, substituted in our original differential equation. So if we let y is equals to vx and dy into this, what will happen is that we have x squared minus x times y. What is our y? Vx plus y squared, which is vx squared, then dx, okay, minus x times a y is vx, then we have dy, which is v dx plus x dv. So in other words, we simply substitute this simple substitution of y and dy into our original differential equation. And from there, we're going to simplify by algebra. So we have x squared minus vx squared plus, this is raised to 2, so we have v squared x squared dx minus, I'm going to distribute this, minus we have uh, x or vx squared. Okay, we have v dx plus x dv is equals to 0. Okay, I can make this as a plus, and I have a negative value here. Okay, that is still the same. Okay, so furthermore, if you are going to solve for that, x squared minus vx squared plus v squared x squared dx, okay, we're going to actually distribute this. So we have negative v squared, okay, v squared x squared dx, okay, distribute this, okay, and then we have negative what? Negative vx cube dv is equals to 0. Okay, we can simplify. As you can see here, okay, I can distribute this. We have x squared dx minus vx squared dx plus v squared x squared dx minus v squared x squared dx minus vx cubed dv is equals to 0. So as you can see here, we can cancel out what? This one, v squared x squared dx minus v squared x squared dx. Okay, that should cancel out. And we are left with, okay, can we still cancel out? No, x squared dx. So here is our answer. Okay, not our answer, but the simplification of this. Okay, minus vx cubed dv is equals to 0. Okay, so we should make this homogeneous equation as simple as possible. So as you can see here, in this equation, we have a common factor of x squared. So if I'm going to multiply this or divide all terms by x squared, what will happen? We will be having dx here minus v dx, okay, minus, okay, vx dv is equals to 0. So what are we going to do? By like terms. So we have, I can factor out dx here. So we have 1 minus v dx minus vx, oops, minus vx dv, okay? Vx dv is equals to 0. So, as you can see here, this is a variable separable equation. Okay? And if I'm going to, again, transpose this on the other side of the equation, this becomes Vx dv. So, this is a variable separable equation. So, we can now, what? Group all terms of v into dv and group all terms of x into x. So, what will happen is that this is dx, this is dv. Okay, I need to eliminate this x on this term, on this side of the equation. I'm going to eliminate 1 minus b on this side of the equation. So I have dx over this x is equal now to v dv over 1 minus b. That is a variable separable equation. And what is the next step? If you are able to arrange a variable separable equation into its corresponding dx and dv, okay, we have to integrate. Okay? Upon integration, we know that integration of ln x, dx over x is ln of x is equal now to, okay, how do we integrate this? Now, my goal is to make this denominator the same as, or to make this numerator the same as the denominator. So, if I'm going to rewrite the denominator or the numerator, I could rewrite this as this, b minus 1, okay, plus 1, okay, over 1 minus v dv. So, this numerator is still the same as equal to v. Okay, if we analyze this, b minus 1 plus 1 is still equal to v. Okay, so the reason I did that is that we can use the properties of integral such that we can separate v minus 1 over 1 minus v dv plus, okay, integral of dv, this is the 1 over 1 minus v. So, if we're going to do that, ln of x, this is simply v minus 1 over 1 minus v. We can rewrite this as, okay, if we factor out the negative sign, we have 1 minus v here over 1 minus v dv plus here dv over 1 minus v. Okay, so you can see this should cancel. So we have ln of x, the integral of negative dv is negative v. Okay, in this integral, if we let u is equals to 1 minus v, du is, okay, negative 1, okay, with respect to dv. So, it means that we have du is equals to negative dv, okay? So, what will happen? Negative dv, I'm going to factor out negative dv here, negative 1 here, and a correction factor of negative 1 here, so that we have negative ln of 1 minus v, okay? So, of course, we have the plus c in here, okay? So, again, if we're going to simplify that, upon simplification, we have ln of x, okay? ln of x plus v plus ln of 1 minus v is equals to c, okay? That is equal to c. So, what will I gonna do is I want to eliminate the ln, okay? Though I could not eliminate an ln here in our v term, but still, if I'm going to exponentialize them, okay? Exponentiate, okay? Raised to something, e, okay? So, we have e raised to c. So, what will happen here, okay? We know that this would be what? This would be equal to e raised to v multiplied by e raised to ln of x plus ln of 1 minus v, okay, is equals to c, still c, okay? And we know also that e raised to v plus e raised to ln of x times e raised to ln of 1 minus v. I forgot to actually rewrite this in terms of properties of exponents. So, we have e raised to v. So, we have times x, e raised to ln of x with cancel e in ln. So, we have 1 minus v here is equals to c. So, in other words, we have e raised to v times x, 1 minus v is equals to c. Okay? But, our term here is v. Okay? We need to substitute back again the value of v into its original. Take note that we have a substitution a while ago that y is equals to vx. So we need to get this in terms of v. So v is equal now to y over x. And if we substitute that in our original, our equation, so we have now e raised to y over x multiplied by x multiplied by 1 minus v, which is y over x, is equals to c. Okay? And if we further simplify this, e raised to y over x times x, okay? This should be x minus y over x, okay, is equals to c. We see here that x will cancel. So we are left with e raised to y over x, okay, times x minus y is equals to c. Now, this is our answer for solving that homogeneous differential equation. Okay? So, we need to substitute back the b upon integration and upon simplifying these terms. Okay, here. so that we could obtain the original differential equation. So let's try again another example. So for number 2, as you can see, solving homogeneous differential equation, it's a very lengthy process, okay? So you have to recall your basics all about algebra and integral, calculus, and of course, your differential, a little bit of your differential calculus, okay? So here is our second example. So as you can see here, we have this differential equation. This is still a homogeneous differential equation because each term has a degree of 2. We have one here, one here. If you add them, that is a total of 2. This is another term with the degree of 2, another term with the degree of 2. Okay? Again, this is m, this is n, again. And what are we going to do here is to simply uh, recognize which is more simpler. So in this case, our more simpler is m, this function. Okay, so what are we going to do if we let, okay, x is equals to vy because m is simpler, then our dx should be, dx is what? V dy plus y dv. Okay, so we're going to substitute all the values of x again here with this substitution vy and all the values of dx with v dy plus y dv. So let's get started. So if we substitute it, x, y here, we have vy multiplied by y. This is x, okay, multiplied by y. And our dx is simply v dy plus y dv. That is our dx. Plus, of course, we have x squared. So can I rewrite it as b squared, y squared already? Right? Because this is raised to 2. So plus y squared, okay, times dy is equals to 0. So if I'm going to we're going to simplify this. B dy plus y dv, okay, plus we have b squared y squared dy plus y squared dy is equals to 0. And distribute this, okay? So we have b squared y squared, okay? Let me just rewrite this. B squared y squared dy, okay? Vy squared times y dv, that should become vy cubed dv plus plus v squared y squared dy plus y squared dy is equals to 0. Can we simplify? Okay, as you can see here, we have by squared dy, b squared y squared dy. We have b squared y squared dy here. We can add them. So we have 2v squared y squared dy. And we can copy the other vy cubed dv, this one, and this one, plus y squared dy is equals to 0. So do they have common factors? Do each term here have a common factor? Yes, we can actually divide them. We have y squared here. We can strip off y squared here. And we have y squared here. So we can divide the whole side of the equation by y squared. So that we have 2v squared, okay, dy plus vy dv, because the y squared here will cancel out. So we have a remaining of y plus simply dy is equals to 0. So combining like terms, okay, so we can have this, okay. Okay, so I can factor out dy. So 2v squared plus 1, we have dy here plus vy dv is equals to 0. So now tell me, is this a variable separable equation? Okay, is this a variable separable? Yes, that is. So if I'm going to rearrange this, this should be dy over y plus, okay, vdv over 2v squared plus 1 is equals to 0. Okay, so what's the next step after arranging this variable separable? Again, we need to integrate. Okay, integrate both sides. So upon integration, we know that dy over y, that's the easiest one. We have the ln of y plus, let me just rearrange or rewrite this v dv over 2v squared plus 1 is equals to 0. So if we let now, okay, if we let now, let u as 2v squared plus 1, du with respect to v is 4v dv, of which this vdv is available on our integral. But we have a 4 here, so you have to offset a 4 here and correction factor outside of the integral of 1/4. Okay? Because just to have a u substitution here. So what will happen here is that we have an ln of y plus 1/4 the integral of 4v dv is du over u is equals to 0. Okay? So if you integrate that, ln of y plus 1/4, okay, ln of u, this would be ln of u, but u is equal to 2v squared plus 1. Now, we integrate both sides here. So we can write a constant here. Okay? So, it's okay. It's always necessary to write a constant because whenever you do integrals. So, it's okay also to write here in the right side. So, most commonly, it is being written on the right side. So, we have now this result. Okay? So, let's first simplify before we eliminate the ln. If I'm going to multiply both sides of the equation by 4, so what will happen is that this should become 4 ln of y plus ln of 2v squared plus 1 is equals to 4 times a constant is still a constant. That should be still a constant. If this is a variable, if you multiply it by a variable, then you should include the variable. Okay? So we have, by properties of ln, we can rewrite this as ln y raised to 4 plus ln 2v squared plus 1 is equals to c. And of course, we can rewrite this properties of ln. We have ln y raised to 4 multiplied by 2v squared plus 1 is equals to c. And if we are going to eliminate the ln, we must exponentiate. Okay? Y raised to 4, 2v squared plus 1 is equals to e raised to c. So we can see that this would cancel. So we are left with y raised to 4, 2v squared plus 1 is equals to still c. Okay? Is this our answer? No, not yet, because it is in terms of v. So if we remember our substitution a while ago, we let x is equals to vy, if I'm not mistaken. Let's just try to see it again. Okay? X is equals to vy. Okay? X is equals to vy. So let's go back to our equation. So here, v would become x over y because of this. So let's substitute it back with v. So we have y raised to 4. Okay, we have 2v squared. What is our v squared? So that is what? 2v squared. We have x squared over y squared. Okay, plus 1 is equals to c. That is our 2v squared. So, simplifying, we have 2x squared over y squared plus 1 is equals to c. And further simplifying this, we have y raised to 4, 2x squared plus y squared over y squared is equals to c. So, we can see that this should cancel. Okay, and we are left with an answer of y squared, okay, times 2x squared plus y squared is now equal to c. So this should be our general solution for our differential equation. Okay? So that would be our general solution. So what if I'm going to, this should be our general, okay? What if there is a condition, okay? This is an add-on problem, okay? If there's a condition when x, let's say, is equals to 0, y is equals to 1. Okay? If there is a condition, as we all know, in solving differential equation, if there is a condition, probably the problem is asking for the particular solution of the DE. So, simply, we're going to find the value of c by simply substituting this value. So we have y squared, that is 1 squared, times 2 times 0 squared. Okay, this should be 0. Plus 1 squared, okay, is equals to c. So as you can see, this should be 1, 0. So our c is equal to 1. Okay? So because 1 times 1 is 1. So hence, our particular solution would be y squared times 2x squared plus y squared is equal to 1. This should be our particular solution. Okay? So particular solution. Okay.